Yeah. So welcome everyone to session R19, the session on query and stream processing. We have 4 talks in this session. The first talk is enabling efficient random access to hierarchically compressed data by Feng Zhang, Jidong Zhai, Shipeng Shen, Onur Mutlu, and Xiaoyong Du. The speaker is Feng Zhang, an assistant professor from Renmin University of China. Please go ahead with the presentation.
Hello, everyone. My name is Feng Zhang. I'm going to present our work on enabling efficient random access to hierarchically compressed data. This is a joint work of Renmin University of China, Tsinghua University, North Carolina State University, and I-ssjoin. This is the outline of our presentation. First, let's look at the background. TADUC, Text Analytics Directly on Compression, is a technique we proposed in VLDB 2018. TADUC can perform text analytics directly on compressed data without decompression. Here, I just gave an illustration. Figure A shows the original files. File 0 and file 1 are 2 files, and WI represents a word. Figure B shows the TADUC compressed data, which uses rules and words to represent the original data. Figure C shows that the rules can be organized into a deck, so the original data analytics can be traversed into a graph traversal problem. Figure D shows a numerical representation, where we use numbers to represent words and rules. Figure E shows the compressed data in numerical form. This is an example of how to perform word count on TADUC compressed data. In the first step, Rule 2 transmits its word frequencies of W1 and W2 multiplied by its rule frequency to its parents, Rule 0 and Rule 1. In the second step, Rule 1 transmits its accumulated word frequencies multiplied by its rule frequency to its parent, Rule 0. In the third step, Rule 0 calculates the final results. By leveraging the hierarchical structure of the compression format, TADUC avoids repeatedly counting text segments that appear many times. Although TADUC provides good performance, it is not efficiently applicable to all text analytics queries. Specifically, such compression-based analytics techniques do not support random accesses. Text analytics is fundamentally based on 2 types of operations on text: traversal operations and random accesses. Traversal operations traverse the entire text corpus. Examples include word count, inverted index, sequence count, and so on. Random accesses, on the other hand, require visiting arbitrary locations in a text document. They are no less common than traversal operations. Previous TADUC only relates to traversal-based operations, but not random accesses. In our daily life, we may need random access operations on data such as news, files, and logs. For example, we may need to search for a certain word or extract a certain piece of data. Based on our analysis, we have summarized 5 common random access operations: search, extract, count, insert, and append. To support these 5 types of random accesses, we'll observe several principles. First, locality. These operations are random accesses to specific locations, which needs the ability to quickly locate the required place. Second, compatibility. We should preserve the compatibility of Taiduk to support previous efficient traversal operations, since Taiduk already supports traversal-based analytics. Third, user transparency. Users should not need to be concerned about the implementation details, but simply use our provided operations. To realize the 3 properties is not easy. We need to handle several challenges. The first challenge is hierarchical structure of the DAG. In the DAG, one node could have multiple parents and may belong to different files. For example, rule 2 belongs to both rule 1 and rule 0, and even in different files. If we want to count the frequency for W1 in file 0, even if we find out that W1 appears in both rule 0 and rule 2, we still cannot tell how many times the word appears in file 0, as rule 2 belongs to multiple files. The second challenge is unidirectionality. Previous Taiduk can only traverse the DAG from the root, since the DAG is a unidirectional data structure. Even if we can locate an interest node, it is difficult to identify the node's sister nodes. The third challenge is spatial complexities on insert. Because a rule may belong to multiple parents and represents multiple pieces of content, we cannot insert directly into the rule. For instance, suppose that one wants to insert W7 right after the third word in file 0. If we insert it directly into rule 1 after W3, the consequence would be that file 1 now have W7 inserted twice at each of the places where rule 1 appears, as shown in the content of rule 0. The fourth challenge is trade-off between space savings and time cost. To support efficient random access, some indexing data structures may have to be added. If the new data structures incur large space overhead, the advantage of the technique will reduce. This figure illustrates the main challenges and our solution techniques. To address the challenges against efficient random access on hierarchically compressed data, we develop 5 data structures: rule to location, word to rule, root offset, bitmap, and records. These 5 data structures are designed to help address the challenges. To address the first challenge of hierarchical structure of the DAG, word to rule and rule to location build the relation between words and offsets. To address the second challenge of unidirectionality, using the first 3 data structures, rule to location, word to rule, and root offset, we can perform local graph works rather than traversing the graph from the beginning location for each random access. To address the special challenge on insert, the bits in bitmap are used to identify why the new content is added in each location, and the new content can be stored separately in records. Finally, to save space cost. These data structures are selectively stored. We show an example of the relations of these data structures in this slide. Route to location and bitmap are separate data structures, which means that each node has these data structures, so they have many instances embedded in each node. The other data structures are single data structures that have only one instance. What to rule and route to location are for entire deck, and the route offset is only embedded in the root node. The extract operation extracts content directly from a compressed file. The rule sequence provides the pointers from children to parents, which enables the random movement from any node in the deck. To extract a piece of content, we can use binary search among offsets to quickly locate the starting unit. Then, after we locate the starting unit, instead of deck traversal, we go through the related rules with the help of the rule sequence data structure until we obtain the required content. The word to rule and route to location data structures can be used for search and count. The word to rule provides a mapping from words to rules. The route to location provides a mapping from each rule to the location. We have special optimizations for the proposed data structures. For example, the figure shows the optimization for route to location, which makes it more compact. We store the newly inserted content into a separate data structure, the record data structure, which contains necessary data for an insertion. For insert operation, it first finds the offset, and then sets the corresponding bitmap and insert the content into the records. Finally, it updates the root offset buffer as the newly inserted content may change the starting offsets of some rules. The append operation also changes data, but it is much simpler than insert, because the new content needs to be appended exactly at the end of a file. We evaluate the efficiency of the proposed support. In terms of both space and time savings. For evaluation, we evaluate the 5 operations with 5 datasets on 2 platforms, including a single node and a Spark cluster on Amazon EC2. We compare our method, compress direct, to the state-of-the-art technique, succinct. This figure shows our throughput results on 3 large datasets. On average, the overall throughput of our proposed technique is 3.1 times of succinct throughput in a distributed environment. We measure the space savings using the compression ratio metric, which is defined as the size of the original data divided by the size of the compressed data. The space-saving results are shown in this figure. The compression ratio of the original Taiduk is high. The newly added data structures inflate the space. However, the average compression ratio we observe is 3.9, which is still much more compact than the 1.8 compression ratio of succinct. Here is our conclusion. We provide a set of new techniques that enable efficient random access operations on hierarchically compressed data. Our techniques are compatible with Taiduk. which supports data traversal operations. We remove a major barrier against the practical adoption of direct text analytics and compressed data. Thanks. Any questions?
Let's virtually thank Feng. Does anybody have any questions for Feng? Let me ask one question to begin with. So Feng, you talked about how your solution has, sort of a much better compression compared to the previous state-of-the-art method. Do you have an idea of how much more additional compression you can achieve? Maybe theoretically, maybe based on some intuition, but still be able to get the performance you need to for random access?
Actually, we can get faster speed for random access because we reuse some redundant data. For example, we use grammar-based compression on the data. We use one rule to represent repeated content. So if two parts are the same, we can reuse the results. For random access, we have index, and the index we can locate the part of the data. We can for the locality reasons, we can quickly locate the content we want to extract or do some analysis. So we can get a better speed.
Okay.
Yeah,
any other
you.
questions for Feng? If not, let's thank Feng for joining in from China for this talk. It's past 3 in the morning. So, Pano, you have a question? Oh, he's clapping his hands. Wonderful. The next speaker for the session is on a talk called Adaptive Overlap Set Similarity Top K Joins. This talk will be presented by Zhong Yang from the Huazhong University of Science and Technology. Again, if anybody has any questions for the speaker, please type them into the group chat box of
Hello everyone, I'm Yang Zhong. I'm very grateful for the opportunity to share our work here. The topic of my presentation is Adaptive Top K Overlap Set Similarity Joins. Speaking of the set similarity join, it usually refers to the threshold-based set similarity join. This join has been well studied in recent years, and it has a broad range of applications. However, the threshold-based set similarity join requires a threshold theta to be manually given beforehand. In modern data systems, such as data lake, there are a massive number of datasets. Users may not have the knowledge to set an appropriate threshold for each dataset. In this setting, the top K join is interesting. The top K join retains K pairs with the highest similarities compared to the threshold-based join. This join has several advantages. First, no manual work is required for finding the threshold. Second, the top K results can help choose appropriate thresholds for the subsequent exploration. In our work, we first focus on the overlap similarity function, and then we extend our work to other similarity functions. The top K overlap set similarity join, TKO-SSJ, is defined as following. Given two set collections R and S, and in an integer K, the TKO-SSJ returns a set of K pairs with the highest overlap similarities. Here is an example. For simplicity, we consider the self-join case. The collection of sets is in the above table. Suppose the value of K is 2. Pair R1, R2, and pair R2, R3 are the top two results, as their overlap similarities are 7, and 6, respectively, larger than any other pair similarities. Next, let's take a look at the top K-join method proposed by Xiang. Top K-join method has the below key points. First, the prefix event. A prefix event is defined like this, where EI is the element at the position POS of the set X, and the TUB is the similarity upper bound that X can achieve from the position POS to the end of X. For example, in the red circle. In this event, E1 is at position 1, and the TUB of this event is 9. And then the priority key, a PQ is utilized to store prefix events in the descending order of TUB, as shown in the figure. Each time after an event is processed, its next event is inserted into PQ. And the inverted index is dynamically built. Once an event of set X is processed, X is inserted into the inverted list IEI. A hash table is used to store the verified set pairs to avoid the duplicate verification. A K-sized heap set is used to keep the largest K pairs have seen. TK gives the K's largest similarity. And the iteration stops when PQ becomes empty, or TK is not less than TUB of the top event in PQ. Here is an example to illustrate the top K method. Let K equals to 2. The set collection is the collection in example 1. At the beginning, PQ is initialized with the first events of all sets. Firstly, event R1E1 is processed, and there is no candidate. R1 is inserted into the inverted list of E1. Then, its next event, R1E2, the event in red, is inserted in PQ. Then the top event is processed, and the pair R1, R2 is found. After verification, it is added into the result set with a similarity of 7. Afterwards, the process continues popping the top events and inserting their next events into PQ, and no new pairs are found. And then, when the event R1E3 is processed, pair R1, R3 is added into the result set with a similarity of 5, and the TK is now updated to 5. And the process goes on. Finally, the event R3E5 is processed. TK is updated to 6. Now TK is not less than the TUB of the top event in PQ, so the process stops. The next part is our proposed fixed step size method. Step size L is defined as the number of sequential elements probed when a prefix is processed. As shown in the figure, the step size is 2. When the event is processed, elements E1 and E2 are both probed. The benefit of using a large step size includes 2 aspects. First, more set pairs are verified in each iteration, so the case similarity in the result set increases faster. Second, the upper bound similarities of the unseen events decrease faster. To help understanding, we explain our idea through comparing the top K-join method and the 2-step size method. The computational cost of the methods includes 3 aspects: scanning the inverted list, candidates verification, and updating in each iteration. Then we can formalize the overall cost of top K-join and the 2SS join methods as the equations. If the indexed entry in both methods are the same. The terms in the red are the same, and so does the terms in the blue circles. Therefore, the cost of 2-I-ssjoin is less than that of top K-join. However, it is likely that the number of the index entries in 2-I-ssjoin is slightly larger, caused by the so-called exceptional case. The exceptional case is defined as below. We use the example in the figure to explain it. In the figure, TK star represents the k's largest similarity in the final results. It is obvious that TK star remains the same regardless of the step size. As shown, L is 2. When the events on the left are processed, the elements in the gray-blue boxes will be probed. But in the top K-join method, the elements in the red area will never be accessed. In this case, these elements are exceptional cases. They will produce additional index entries in 2-I-ssjoin method. And it is worth noting that the exceptional case happens at most once in each set. In another case, when the events have TUB minus L equals to TK star, there will be no exceptional case. As shown in the figure, the events has TUB minus 2 equals to TK star, so there is no exceptional case. To this end, we can deduce that the number of exceptional cases, denoted as NEC, is no larger than the size of X, where X is the collection of sets whose lengths are larger than TK star. NEC is small compared to the total number of the index entries. Therefore, the cost of 2-I-ssjoin is less than that of the top K-join. Similar to 2-I-ssjoin, cost model of L-ssjoin is as shown. The range of NEC can be represented as the figure. The triangle in the figure represents the set collection. The different Ys represent sets with different sizes. The gray-blue part represents the elements must be accessed, and the green part represents the possible exceptional cases. As mentioned before, in 2-I-ssjoin, NEC is no larger than the size of X. And then in L-ssjoin, NEC is no larger than L minus 1 times of X size. We notice that with the increase of L, NEC may increase, so there is a trade-off between the benefit of a large step size and the additional cost caused by the exceptional cases. There exists an optimal step size to achieve the best performance. The optimal step size L is difficult to determine for different datasets. To address this problem, we propose the adaptive step size method. In the adaptive method, L is enlarged round by round at the beginning and bounded by the upper bound LUB, where LUB is dynamically updated by TUB minus TK. Where TUB is the current upbound similarity in PQ, and the TK is the current case similarity in result set. Besides, we also introduce an event-based verification to avoid redundant computation in the verification phase. Next, we extend the method to other similarity functions. The major changes are TUB and LUB shown in the table. We conducted the experiment on 6 real-world datasets. The statistics of the datasets are shown in the table, and the distributions of 3 of them are shown in the figure. We compare the following algorithms: all-pair, PP-join plus, group join. These are the classic threshold-based join algorithms. We extend them to adapt our problem. The overall performance with K of 500 is shown in the table. The result indicates that our step size methods always achieve the best performance. We also draw the comparison on running time with different K. The running time increase is with the increase of K, which is as expected. And the below figure is running time with different step size. And this figure shows the trace of the number of the exceptional Ks with different K and the step size. We also conduct several other experiments. Due to space and the time limit, they are not shown in the slides. Last of all, we draw the conclusion that our proposed algorithms performs the baseline through extensive experiments on large scale of datasets. That's all my presentation, and thank you for your attention.
Great. Let's thank the speaker. So there is one question from the audience for the speaker. Guilherme, would you like to ask your question yourself? I can unmute you.
Yes, of course. Thanks for the question. It's a good question. The index adding is stopped when the algorithm stops. So there is no additional stop condition of the index. This is a good point. I think we can consider the optimize of the index in our further study. Thank you.
Do you have an answer for that question?
Did I explain clearly?
Yeah, I think so. I think Guilherme says thank you. Any other questions for the speaker? If not, let's thank Jongyang again. The third talk of this session is called Load Shedding for Complex Event Processing, Input-Based and State-Based Techniques. The paper is by Bo Zhao, Quoc Viet, and Matthias Weidlich. And this talk will be given by Bo Zhao, who's a PhD student from Humboldt University of Berlin, Germany.
Hello, everyone. My name is Bo Zhao. I'm from Humboldt University of Berlin, Germany. Today, on behalf of my co-authors, I'm going to talk about load shedding for complex event processing, input-based and state-based techniques. Complex event processing systems continuously evaluate queries over high-velocity event streams. It usually defines a sequential pattern of events which are correlated by a value predicates within a time window. There are a lot of applications, including finance, fraud detection, smart grid, transportation, and Internet of Things. CEP queries requires low latency and high throughput. We explain a CEP query by an example of bike sharing in New York City, where users rent bicycles through a smartphone application. They search bikes at nearby stations, start rides, finish trips, and log bikes at destinations. Bikes may quickly accumulate in certain areas. Therefore, the operator moves around 6,000 bikes per day among stations. To improve operational efficiency, we detect hot passes of trips. The operator should relocate bikes among hot passes. This query specifies a pattern that the previous trip's end station is the next trip's start station within 1 hour. One hot pass is illustrated in this figure. CEP query processing is stateful. It maintains a set of partial matches per query. State may grow exponentially in the number of processed events. It may face dynamic workloads, where input streams may change by orders of magnitude during short peak times. As demonstrated in figure 2, and this overload situation is hard to predict. This makes low latency evaluation very challenging. To solve this issue, there exist a lot of optimizations, including parallelization, pattern sharing, efficient immediate representation for partial matches, and semantic query rewriting. However, they have the limitation that it is difficult to pre-allocate resources for unpredictable short-time spikes. Exhaustive low-latency evaluation becomes infeasible. Therefore, we consider lossy optimizations for best effort evaluation. They usually discard some input tuples. However, dropping input tuples usually generate low-quality results. We illustrate this issue by the same example of detecting hot passes of backsharing. A trip is denoted by a pair of start station and end station. Trip from 5 to 8 at time point 1 contributes 0 complete matches. This should be discarded. However, we want to keep the same trip at time point 5 because it contributes 2 complete matches already for time window 2, 3, and 4. We now define the problem of CEP load shedding. It is to ensure that when evaluating a CEP query for a stream, it holds that the latency is below a predefined threshold, such that the lossy results caused by load shedding is minimal. We can perform input-based load shedding. It has cost granular control of shedding impact. However, it saves more computing efforts because it directly discards input tuples and does not generate any partial matches at all. State-based load shedding, on the other hand, drops partial matches. It has fine granular control of shedding impact. However, it saves less computing efforts since a partial match has already consumed some computational efforts. Hybrid load shedding has the potential to combine the advantages of both input and state-based load shedding. To perform load shedding, we need to solve 3 problems. The first problem is to decide when to trigger load shedding. This is solved by monitoring CEP system's latency to decide whether it is above a predefined threshold. The second and third problems are what and how much data to shed. This is achieved by a cost model and the algorithm of shedding set selections based on it. The cost model considers 2 aspects of a partial match, its contribution and its consumption. Contribution assesses the contribution of a partial match to the query results. It is defined as the number of complete matches derived from it. Consumption assesses the computational resources consumed by a partial match. It is defined as the computational resources for all its derived partial matches and complete matches. We now introduce how to select the shedding site. For a partial match P in all maintained partial match site, we consider its relative consumed computational resources as a ratio of its own consumption to the consumption of all partial matches. We denoted it as delta minus. It is linked to latency saving. Similarly, we also consider the loss of complete matches. Therefore, we define the shedding site selection as an optimization problem of partial matches. It is a kind of knapsack problem, which is NP complete. It should be noted that any decisions of load shedding must be made instantly. Therefore, we discuss optimizations to solve shedding set selections, especially to reduce the search space. To this end, we consider the granularity of cost models and lift it by temporal abstractions and data abstractions. For temporal abstractions, we divide the time window into several intervals or time slices. consumptions and contributions are computed per time slice instead of per time point. Similarly, data abstractions observe that partial matches of overlapped attribute values may have similar consumption and contribution values. Therefore, we lift the cost model to classes of partial matches instead of individuals. After this, we can generate state filters and input filters to perform the actual load shading. State filters are generated directly from the partial match shading side as a lookup table. Input filters can be derived from partial match shading side by cross-checking the event schema and value predicates. There is a major problem of computing contribution and consumptions of partial matches. That is, they can only be computed in retrospect because we are talking about computing something in the future. Therefore, we need to estimate them. We first estimate the cost model offline and then adapt it online. For offline estimation, we record historical partial matches and complete matches. Based thereon, we derive contributions and consumptions for partial matches. After that, we perform clustering for partial matches based on contribution and consumption values per time slice. The contribution and consumption values for each cluster are computed as the 90th percentiles of the value of the partial matches within that cluster. We keep a map of cluster labels and these values to use a classifier to use the class estimates in online processing. We train classifiers for the partial matches of the clusters, one classifier per state. The classifier uses as the attributes of partial matches that appear in the query predicates. For online adaptation, initially we start with the classifiers obtained from offline estimation and the mapping of cluster labels and contribution and consumption values. However, the contribution and consumption values may change as time goes by. Therefore, we monitor and update these values by streaming counts, such as sketches. We maintain the contribution and consumption per class by a lookup table for each state. We evaluated 6 queries of 2 synthetic datasets and 2 real-world datasets. We compare our hybrid load shading against 4 baseline approaches. They are random input shading, selectivity-based input shading, random state shading, and selectivity-based state shading. We measure the result quality and throughput performance. We implemented an CEP engine in C++. Evaluations of synthetic datasets were conducted on a workstation. For real-world datasets, we evaluated them on a powerful Newman machine. Let's first look at the overall effectiveness and efficiency. As shown in Figure 4a, state-based strategies yield better recall due to fine granular shading. Figure 4b illustrates that input-based techniques yield higher throughput. Hybrid approaches strives for both higher recall and throughput. From Figure 4c, 4d, and 5a, we observe that hybrid approach prefer state-based shading for relaxed latency bound, that is above 500 microseconds. However, when the latency bound became tighter, as below 500 microseconds, hybrid shading prefers to drop input tuples. Next, we evaluate the effectiveness of shading data selection compared to other 4 baselines. Input-based shading with our cost model yields better recall than random-based and selectivity-based input shading. We observe the same for state-based shadings. We now evaluate the impact of variance of query selectivities. we control the variance by value distributions. The recall is not affected, and hybrid shading leads to the highest results. For low variance as x equals 2, the hybrid approach precisely assesses the utility of input tuples and discards irrelevant ones, significantly improves throughput up to 120 times. Next, we investigate the impact for temporal granularity. The increasing number of time slices improves recall for hybrid shading, but it significantly decreases the throughput. Next, we consider the impact of cost model estimation. Generally, recall is not very sensitive to the number of clusters. More clusters lead to higher recall, but only until reaching a certain number of clusters. In this example, that is 8. We also tested the adaptivity of the cost model. We consider the worst case testing. We change the distribution of attribute values upside down, which means we reverse the cost of partial matches. The quality of query results suddenly drops to 0 and gradually converges to normal level. We can observe this V shape in the plots. Convergence is quicker for smaller window size because it has a shorter lifespan of partial matches. Finally, we examine 2 real-world case studies. One is backsharing in New York City, and the other one is Google cluster monitoring. They have the same trend as synthetic datasets. Hybrid shading yields highest recall. In backsharing, the throughput of hybrid load shading is comparable to state-based shading. However, in Google cluster monitoring, it is comparable to input shading. After a further investigation, we found that this is because backsharing prefers state-based shading, but Google cluster monitoring prefers input-based shading. It shows that different applications may favor different shading strategies. That's it. Thank you. I'm happy to take any questions.
Let's first thank the speaker, Bojang. Anybody have any questions for him? So I have one question, Bo. You talk about load shedding, whether it's input shedding or partial match shedding, in terms of completely discarding the input or the partial matches. Suppose you have the possibility that there are subsequent times where your resource utilization is very low, right? Would it make sense to, instead of shedding the data, to just keep it in some backup buffer and read it again at a time when you have more resources to spend on those data?
Yes, thanks for the questions. So the main object we want to achieve is a low latency. So if we store the partial results at the buffer, then the latency actually accumulated. So we don't want to have this situation.
Correct, but partial results may contribute to subsequent results much later, right? So even if you retrieve a partial result from a buffer, it's not as though it contributed the final result right away. It may contribute the final result only, 10 seconds later, at which point there is no latency, right?
Yes, I mean, that is also true, but I mean, even for the partial matches that will actually contribute, we also have this exponential blow up. So I think those 2 approaches are actually orthogonal together, so they can coexist actually.
Okay. Any other questions for Bo? If not, let's thank Bo again for a nice talk. So the final talk of this session will be SPER, Expediting Stream Processing with Accuracy Guarantees. And the authors are Nikos Katsipoulakis, Alexandros Lavrinidis, and Panos Chrysanthis. The talk will be given by Nico. Nico is a software development engineer at Amazon Web Services working on Redshift. And he's told me he's stuck outside the country right now somewhere because of coronavirus, I guess. So Nikos, go ahead with your presentation, and then at the end, we'll take questions.
Hi, my name is Nikos, and I will talk to you about SPER. SPER is a prototype system for expediting stream processing while offering accuracy guarantees. This work is part of my PhD thesis and was completed with the support of my academic advisors, Alex Labrinidis and Panos Chrysanthis. Nowadays, stream processing is used for monitoring applications or continuous ETL. As a result, stream processing engines, or SPEs, are optimized for continuous operation on statically allocated resources. For this talk, imagine that a vehicle fleet of a ride-hailing company produces a data stream whose tuples consist of a timestamp, a fair amount, and a route ID. A typical use case is to pre-aggregate the stream's tuples before pushing them to another system. Our example's query produces each route's median fair value on 10-minute windows with a slide of 5 minutes. Windowing is used in order to avoid depleting available storage. This query's logical plan consists of a source, a window, and a median operation. Depending on the SPE, the window and the median operations can be fused together to avoid network I/O. Window operations require storing tuples and defer processing until a window is complete. This happens when an operation receives a watermark, which is a control tuple containing a timestamp sent by the source. Next, the logical plan is turned to a physical plan by assigning its operations resources. In order to cope with data production rates, a user employs parallelization to handle each operation's load. In our example, the physical plan consists of two ingress operators which partition data to data stream window operators. In turn, 3 operator instances are responsible for producing window results. Each operator instance corresponds to a worker thread with access to limited main memory. All threads have access to a global secondary storage, which is often a cloud-hosted, globally accessible file system. Cloud storage serves for either priming a recovered worker state or storing a worker's data when those do not fit in main memory. At tuple arrival, each worker stores tuples in main memory until they are fully processed. If at any point in time a worker's memory becomes full, then the worker has to spill overflowing data to secondary storage. The single buffer design keeps all tuples in an unsorted buffer. When a new tuple arrives, the worker appends it on the buffer. This design uses minimal amount of storage space. At watermark arrival, a completed Windows tuples are prepared for processing. Also, any fully processed data need to be evicted and have their memory reclaimed for future use. With a single buffer design, the buffer is scanned once and all tuples corresponding to the complete window are sent for processing. In addition, expired tuples are evicted. In the example shown, watermark with timestamp 69 triggers the processing of a window from timestamp 50 to 65. Hence, the worker scans the buffer and stages all corresponding tuples for processing. In addition, it evicts all tuples that have expired. In this work, we focused on the single buffer design as it offers minimal memory usage and optimal write amplification. The problem that most SPEs face materializes from the mismatch of assigned resources and the needed processing capacity. SPEs resources are assigned at query submission, but incoming data volume can change over time. On the one hand, a user can over-provision resources without utilizing them. This leads to unnecessary operational costs. In the example shown, the 3 workers can efficiently process 3 units of input. If the input consists of 4 units in total, then allocating 3 workers will lead to unnecessary operational costs. On the other hand, if not enough resources are available, the SPE will miss its delay target. In the example shown, a worker input cannot be accommodated in the total storage available to 3 workers. Thus, each worker has to spill load to secondary storage, which results in performance degradation due to paging. Our work aims at reducing the probability of missing delay targets when provisioned resources cannot cope with data volume. Resource allocation in SPEs is a hard problem, and many solutions have been proposed in the past. Load setting involves dropping data when the underlying infrastructure is not capable of meeting the delay target. However, to the best of my knowledge, existing solutions cannot provide accuracy guarantees for rapidly changing data. Sketching solutions are able to reduce memory requirements by introducing additional computations per tuple. Nevertheless, sketches cannot be applied to many problems, and reconstructing a result requires additional memory. Incremental processing techniques have been shown to reduce resource usage. However, they cannot be applied for holistic aggregate operations. Finally, elastic SPEs have been proposed to deal with the static resources problem. However, those are appropriate for long-term spikes and are inefficient when applied on sudden bursts. Current SPE workers' main memory-centric design is problematic. The resource allocation problem stems from trying to fit all active data in main memory. This approach will further decrease performance under overloaded situations, since it initiates interaction with secondary storage. In contrast, we propose a frugal processing model which uses secondary storage as the main storage unit and processes only the fraction of the data that are needed. Our model's goal is to try to provide a valid answer with what can fit in main memory at overloaded situations. Inspired by approximate query processing, or AQP, SPER maintains performance by processing a fraction of the data. SPER's queries require an accurate specification, which consists of an error and a confidence. Accuracy works as an upper bound for the allowed error when window results are approximated. In addition, a memory budget B indicates the space that each SPE worker is allowed to use for approximation. Previously proposed AQP systems rely on either offline or online sampling with known data properties. Both of those are infeasible in SPEs due to the uncharted nature of incoming streams. To this end, SPER relies on incremental sampling and gathering of data properties. The memory budget's usage differs depending on the operation. For scalar operations, B is used to accommodate a uniform sample, whereas for grouped operations, B is used to gather data properties. Those properties will be used to construct a stratified sample at window completion. When a window is complete, SPER estimates approximation accuracy given a memory budget. In case the accuracy standard is not met, then SPER processes the whole window. Each worker carries a buffer B for each window. Its new tuple is stored either in the main buffer, the secondary buffer, or both. For scalar operations, a worker maintains a uniform sample with the values participating in the aggregate operation. In our example, for each window that a tuple participates in, a reservoir sample of size B is updated accordingly. For grouped operations, a worker needs to build a stratified sample of the tuples that belong to a window. This sample should include a proportional number of tuples for each group. As I mentioned earlier, incoming data characteristics are unknown. As a result, each worker can only use B to maintain statistical information for each group. This mainly includes each group's frequency. If B is not enough to accommodate group's information, then the worker marks the window as unsafe for approximating. In this case, a window's result can only be produced from all the data. At watermark arrival, a window is complete and the worker has to stage tuples for processing. At this point, a SPER worker decides whether B's contents can produce an approximate result within the desired accuracy. For scalar operations, the worker scans B and produces an accuracy estimate along with an approximate result. If the estimated accuracy is less or equal to the desired accuracy, then the approximate result is used as the window's result. Otherwise, the whole window needs to be processed. In the latter case, SPER's overhead consists of scanning B. For grouped operations, SPER has to estimate the sampling frequency of each group. Thus, it scans SPE's contents and determines the sampling rate of each group. If the estimated accuracy is within the accurate specification, then it scans the buffer to produce the stratified sample and the approximated result. This scan is piggybacked on the scan for tuple eviction, which is required for the buffer design. Finally, it produces the approximate result as the Windows result. In any case, SPE's overhead is O of B, which is bounded to the number of distinct groups in the window. Finally, I will present some experimental results. All experiments were conducted on an AWS cluster. In our experiments, we used 3 datasets that come with time-based sliding windows. We analyzed all datasets' window stats offline to find out p-values which would allow approximating a significant portion of all the windows. One of the datasets features the scalar holistic aggregate operation, and the other 2 grouped algebraic aggregate operations. As accuracy, we used relative error, which was set lower than 10%. The confidence was set to 95% or more. First, we measured SPE's ability to scale with a varying number of workers on the same query. For this experiment, we compared Storm and SPE's average window processing times and average tuples processed by its worker. It is clear that SPE offers a much lower processing time as it processes only tuples that can fit in B for all windows. This is plotted on the graph on the right, which shows the average number of tuples processed by its worker on each window. SPE workers process up to B tuples on each window, whereas Storm workers have to process all tuples of every window. Next, we fixed the number of workers to 4 and measured the average window processing time for the datasets with a grouped operation. In both datasets, SPE presented a much lower processing time compared to Storm. Similar to the previous scale experiment, this is due to the reduced number of tuples that SPE has to process. SPE relies on its ability to decide on the safety of approximating a window given a budget value. This ability relies on the accuracy estimation mechanism. In order to quantify this mechanism's success, we conducted the sensitivity analysis with a DEC dataset and varying B values. For processing a scalar mean, we set the relative error to 10% and pick 3 budget values. A low budget value, which we expect SPE to identify as too low to produce an accurate result. A medium budget, which we expect SPE to allow for more approximated results, but with some errors. And an approximate budget value, which will allow all windows to have an approximated result and with a valid accuracy for all windows. First, I present the results with a low budget of 250 tuples per worker per window. The graph shown presents the relative error across all windows. The x-axis is the progress of all windows. The red horizontal line is the 10% relative error mark. The blue line is the actual error of each window result produced. When the blue line has a 0 value, this indicates that SPE decided that the window's results cannot be approximated with a given budget. When the budget is low, SPE approximates a small fraction of the windows. In addition, some of them achieve an error more than 10%. With a medium set budget, SPE approximates the result of almost all windows. In addition, in the majority of the windows, SPE's estimate is correct as it leads to a relative error of less than 10%. In some cases, the error is more than the requested accuracy, but still within the confidence specification. Finally, when the budget is set to the appropriate setting, SPE approximates all windows correctly. Its accuracy estimation mechanism is successful, and all windows results have a relative error within the accuracy specification. As a result, SPE is able to react to changes in data and preserve the defined accuracy specification. In conclusion, resource allocation is a hard problem in the context of stream processing. SPEs underperform when input spikes occur. SPE shifts the processing paradigm of current designs and aims to postpone resource reconfiguration or performance drop. Finally, I invite you to read our paper for further details. Thank you.
Let's thank Nico. Does anybody have questions for Nico? So Nico, I have one question to start. You talk about the case where you have sliding windows, right? So there is substantial overlap between the contents of neighboring windows, the neighboring sliding windows, right? So do you observe that the errors that you see on adjacent overlapping windows, that they are somehow correlated?
So that's a very good question. The thing is that with the current stream processing engines design, usually the tuples for each window do not necessarily interfere with each other. However, in order to avoid like temporal locality or temporal bias in our sample, or reservoir sampling for each window, and the replacement takes place at the window context. So essentially, as I mentioned in my talk, we maintain a memory budget or a B for each window in order to avoid having, bias based on like tuples that appeared in one particular point of time and dominated the key space or the value space.
So essentially, if I understand correct, for every sliding window, even if you slide a window of length 1000 by one tuple at a time, you have to independently resample from that window? Or do you share samples across windows, across the sliding windows?
No, we don't share. Like the sampling takes place independently for each window with a so we haven't explored ways of sharing samples or incrementally like getting shards of samples and combining them to, but that actually might be an interesting way of mitigating the cost of sampling in SPER in the future.
Correct, because if you do that, you can potentially share work and get higher throughput and lower latency as well.
Not only that, it would actually help also in the accuracy estimation mechanism. I didn't dive into the details in the talk, but there are more details in the paper. As a long story short, like the accuracy estimation is specific for its type of aggregate. And because we use normal approximation for instance, the average, using incremental ways of sampling or resampling can actually help us better in the accuracy estimation of a window result. So that's actually what you mentioned actually makes sense for two reasons. First, to not pay the performance cost of sampling for its window, but also to come up with better accuracy estimation.
Thanks, Nico. There are a couple of other questions from the audience. So the first question is from Danny Shi. Danny, would you like to ask your question yourself? You can, let me see if I can unmute you. Or let me ask on behalf of Danny. The question is, could you elaborate more details about the purpose of secondary storage? Sorry, Danny.
Sure. So secondary storage is kind of like fail-safe mechanisms for all stream operators or stream workers in stream processing engines. And for our study, we looked at Spark Streaming, Flink, Storm, and Heron, which they use secondary storage for fault tolerance in case a worker dies, in order to restart a worker to meet the tuples that haven't been processed. But also, it's a way of like a distributed log of keeping track of what its worker has done, and that comes back into provenance. It might come back to be able to query the data on in offline fashion or even like load them into an OLAP system or a system that you can query directly log files like Spark SQL or whatever.
Okay, so the secondary storage is more like an offline storage that you can query more specific data. Is that the purpose of it?
So for the stream context, it's more of like, recovery source. But also in some cases, if, as I mentioned, each worker is a JVM process, a JVM thread. If you run out of memory, of heap memory, you're either going to crash or you're going to effectively like use additional resources to not crash. And crashing in real-time processing can be very bad because you actually start losing data. So it uses as kind of like a secondary storage to start paging and utilizing it so that you don't crash your worker.
Okay, thank you.
So we have another question from the audience. I think Ida Shashbalaki asks, how do you set the window length?
So the window length is on the query definition, at least in Storm and to some extent in SPER. It doesn't come with a nice functional way as you define windows in engines like Flink or Spark, but it's set at query submission, and then it stays the same for the duration of execution until you stop, processing data.
Ida, does it answer your question? Yes, good. Any other questions for Nikos? All right, let's thank Nico again. So that concludes this session. And I guess that concludes the recording as well. But if people would like, so I guess somebody can stop the recording.